Hi class, we continue our study in chapter 13 talking about vector functions by moving into section 13.3 talking about arc length and curvature. Okay, so first let's talk about length of a curve. So we've defined the length of a plane curve with the parametric equations x is equal to f of t and y is equal to g of t. Here just looking from a to b, all right, as the limits of the length of inscribed polygons. And for the case where the two derivatives are continuous, we arrive just at this formula here. So this was a formula from previous section of our class. All right, just talking about arc length here, basically, okay? So what we can say is the length of the space curve is defined exactly the same way, okay, for a space curve. So suppose that that curve has the vector equations r of t given by f of t, g of t, and h of t, or equivalently the parametric equations x is equal to f of t, y is equal to g of t, and z is equal to h of t, again where their derivatives are all continuous. If the curve is traversed exactly once as t increases from a to b, then it can be shown that its length is just the following here. Okay, so all we're doing here is taking our formula here and replacing these parts here just with the derivative of the components of the vector, okay, from the vector function. Okay, so notice that both the arc lengths formulas in the previous two can be put in a more compact form. So we've learned this before, that arc length is equal to the integral from a to b. Here now, what's different about this is this right here is just the formula for the magnitude of the vector. Okay, so in this case, it's the magnitude of the derivative of the vector valued function. So the arc length is equal to the integral from a to b, the magnitude of r prime of t dt. Okay, so that's just the arc length formula here for a vector valued function. All right, let's do an example. Okay, so find the length of the arc of a circular helix with vector equations. So r of t, the vector valued function, is cosine of ti plus sine of tj plus tk. Okay, and this is from the point 1, 0, 0 to the point 1, 0, 2 pi. Okay, so first thing we're going to do, to find this arc length here, we need to find the derivative of the vector valued function. So we see that the derivative of cosine is minus sine of t, derivative of sine is cosine, and derivative of t is just 1. So the next thing we're going to do is we're going to take the magnitude of this, okay? So it's the square root of the first component squared plus the second component squared plus the third component squared. Well, what's going to happen here is you're going to see sine squared of t plus cosine squared of t is equal to 1 plus 1 squared here gets you 2. So the magnitude of r prime of t is just the square root of 2. All right, so from the arc from this point, so they're telling you from the point 1, 0, 0 to this point 1, 0, 2 pi. Okay, how do you know what interval or bounds of integration to pick? Well, this one's actually really easy because one of the parameters, or one of the components, excuse me, is just t. So it obviously starts at 0, and then it just goes to 2 pi. So when you integrate this, we're going to replace the magnitude of r prime of t just with the square root of 2. Piece of cake, this just integrates to the square root of 2 times t. Well, fundamental theorem of calculus, our answer just ends up being 2 square roots of 2 pi. And that's it. So that's the arc length along this circular helix from this point to this point right here. Okay, now what we might want to do, and this is where it gets a little bit harder, is have a function. Okay, find a function that will give us the arc length. Okay, so now we suppose that c is a curve given by, again, this vector valued function, okay, where r prime is continuous and c is traversed exactly once as t increases from a to b. Then we can define this arc length function here, okay, and it's s of t. Sometimes we'll just denote it as s of t is equal to the integral from a to t, all right, magnitude of r prime of u du. Okay, it's a little bit different here. Okay, so just remember this here. Notice what we do is we have some starting value, and then notice that our upper bound of integration t, it's not a number, it's going to be the variable t. Okay, so thus this function s of t is the length of the part of c between where we're starting a and some other t that we can pick whenever we want. Okay, and it's just going to be, the function is going to give this length here. Okay, if we differentiate both sides of the equation 6, okay, using part 1 of the fundamental theorem of calculus, we just get the following. ds dt is equal to the magnitude of r prime of t. Okay, so it is often useful to parameterize a curve with respect to arc length because arc length arises naturally from the shape of the curve and does not depend on a particular coordinate system. All right, so let's do an example here. Okay, let's reparameterize the helix r of t is equal to this cosine of ti plus sine of tj plus t of k with respect to arc length. Okay, so we want to reparameterize it, and I'll get to that. All right, measured from 1, 0, 0 in the direction of t increasing. Okay, so the initial point 1, 0, 0 we saw corresponds to the parameter value t is equal to 0. So that tells me my bottom bound of integration. Okay, so my upper bound of integration t here, okay, is going to stay. So s is equal to, that's why I said sometimes just called s, a function of t. We're going to integrate from 0 to t, the magnitude of r prime of u now, okay? So we're going to take this function, okay, and we're going to integrate it with respect to u now, okay? So when we integrate that from 0 to t, the integral of t du, this just becomes, the square root of 2, square root of 2u. Well, you plug in 0, it goes away. You plug in t. So s of t, okay, my arc length function is equal to the square root of 2t. And that's it. All right, so therefore, just by reparameterizing it here, what I'm going to want to do is get t by itself. Okay, so I'm going to divide over the square root of 2. Okay, and wherever I see a t, I can put it in terms of s now. Okay, and the required reparameterization of this is obtained by substituting for t. So I'm going to take my r function, okay, and plug in t, which is now a function of s. So wherever I saw a t, I'm just going to put s over the square root of 2 in my original function here. And what that's going to do, okay, is that's going to be able to tell me where I am on the curve given any length s. So that's just why we reparameterized it that way.